Hi, and welcome to the video for section 5.3 for Math 181. This is the only video for this section, first video of one video. In section 5.3, we're going to be evaluating definite integrals. So in the last video for section 5.2, I kind of gave you guys the shortcut method of how to evaluate the integrals instead of the long formula that you would normally have to go through. That's essentially what this chapter, or this section is doing, is just presenting it in a formality, and then a bunch of examples that we'll do. So the shortcut I gave you actually has a name, and it's called the evaluation theorem. And it says the following, that if f is continuous on the closed interval ab, then the integral from a to b of fx dx is just equal to, so we take the antiderivative, and then we evaluate that at the value b, the number on top of our integral, minus that function that we determined, evaluated at that point a. And this is where f, capital F, is any antiderivative of little f, which is to say, i.e., f inverse is equal to f. So again, it's putting into a formal statement what I showed you guys at the end of the last video. So let's look at an example. Start with a real basic one just to kind of remind you what's going on here. So let's say we have an integral from 0 to 1, and we're integrating x squared dx. So the first thing we're going to do is take the antiderivative of this x squared. So what do? Well, we add 1 to the exponent, so 2 plus 1 is 3, and then divide the coefficient by that exponent, so 1 over 3. So the antiderivative of x squared is 1/3 x to the third. And then we're going to use the notation, we just draw a straight line, and we put these numbers here, 0 to 1. So now that we've taken the integral, we want to give ourselves some sort of notation that, all right, we've already done that part of the work, what's left to do? And it's evaluated at these points. So by this evaluation theorem, we're taking this function evaluated at 1, so it's 1/3, 1 to the third power, minus 1/3, 0 to the third power. So we just plug in 1, we plug in 0, we take the difference of the two. This one, of course, goes to 0. So it's just 1/3 times 1 to the third power, which is just equal to 1/3. So the proof for this guy, and again, you guys know me by now, I'm not going to use video time going through proofs or derivations of formulas. But if you want to see it, the proof is on page 282 and 283. Actually showing you why does this work, why can we utilize this shortcut. So let's look at a couple more examples. So in this example, we want to evaluate the integral from 1 to 3 of e to the x dx. Alright, so using the same idea we did here, first we want the integral, the antiderivative of e to the x, which is what? Well, again, it's just e to the x, same thing. Derivative of e to the x is e to the x, so going backwards, same value. Draw our line for notation, we're going from the point 1 to 3. So So now we plug those values in. So we have e to the third minus e to the first, and that's really it. If you have a calculator, you could probably calculate it. If it's asking you for an answer to a certain number of decimal points, you could do that. But otherwise, you're basically done. The integral from 1 to 3 of e to the x dx is just e to the third minus e to the first. And another example, let's say we're going from 0 to b of cosine of x dx. So we want the integral, the antiderivative of cosine of x. So what function, when we take its derivative, gives us cosine? Well, that's sine. So sine of x, and we're evaluating it from 0 to b. So we do the same thing, plug those in. Plug in b here, so we get sine of b minus sine of 0. Well, sine of 0 is what? It's 0. So this whole thing just simplifies to sine of b. So depending what value we pick for b, if we choose b is equal to pi over 2, then from 0 to pi over 2, our answer would be sine of pi over 2, which is just 1. So by leaving this general value on top, once we choose what that value is, it will give us different answers. All right, so that was evaluating definite integrals, meaning that we had some values on the integral sign. And remember, we have the indefinite integrals. And that was the integral of f of x dx is equal to some capital of f of x where f prime of x gives us little f of x. So the difference between these two, and this is important to note, is that what? When we were doing definite integrals, so here's a note, important to know here, a definite integral is a number. It's telling us what? It's telling us under area under a curve. So it's an actual number. An indefinite integral is a function or a family of functions. So depending what you're given as a problem, if you have actual values on the integral symbol, you should end up with a number. If you're given just the integral symbol, no points on the top or bottom, you should end up with a function. And don't forget, you're usually going to have that plus c in there as well. So on page 284, there's a whole table of indefinite integrals. But it's basically the same thing that you had in your antiderivative tables at the end of chapter 4, I believe it was. So again, you can go there, you can reference it. Maybe it has some that you didn't have before in your table. I'm not going to list them here because we already did that in an earlier video. But if you go to page 284 in the book, it has this table of indefinite integrals. So let's look at the distinction between the two, just two examples here, and that'll wrap this up. Let's say we want to find the integral of 10x to the fourth minus 2 secant squared x dx. So in this case, we have what? We have an indefinite integral. We don't have values on here to evaluate at the end. So all we're going to do is we should end up with some function. We're not going to end up with a number. And so remember, from our antiderivatives, we're just going to do each of these separate. So for 10x to the fourth, our antiderivative, our integral is what? We add 1 to the exponent and divide the coefficient 10 by 5. That's the first part done. Minus 2. And then what is our antiderivative of secant squared? Well, that's tangent of x. And are we done? No. Why? Because we have to put in our plus c. So maybe you're asking, like, if we have a definite integral, why didn't we have to put in plus c? Well, what were we doing? This is a constant. So we were evaluating the function at one point and then subtracting the other. So if I had whatever, x squared plus c, and then I plugged in some number here and then subtracted some other number, well, what happens? The c's cancel each other out. So we didn't have to really worry about it in that case. But for indefinite integrals, we need to put that c in there because there might be some other value at the end that when we took the derivative, just dropped off to 0. So if I just simplify this, 10 divided by 5 is 2, so 2x to the fifth minus 2 tangent x plus c. So that's a function. We had an indefinite integral. Once we take that integral, we end up with a function. Let's look at one more example. Let's say we want to evaluate the integral from 0 to 3 of x to the third minus 6x dx. So you can see a little bit too. This one says what? This one says find this integral. This one says evaluate that integral. So when you see evaluate, you should think I need to plug these values in. So if we take the integral of each of those pieces, well, we have what? X to the fourth, exponent goes up by 1, and then 1 over 4, and then minus, so the exponent goes up by 1, so 2, 6 divided by 2 is 3. And again, we're not going to worry about the c here because once we do plus and minus, it cancels each other out. So the key now is to evaluate this from 3 and 0. So if I plug in 3 to begin with, I get what? 1/4, 3 to the fourth power, minus 3, 3 squared. So that's my f of b. So my b is 3, so I plug in 3 to begin with. Now I need to subtract, and don't forget to do this, the f of a. And be careful here. I would suggest using parentheses because with this minus sign, if we end up with some minus values somewhere, it's going to, we have to account for that to make sure that we're not subtracting when we should be adding or vice versa. In this case, it won't matter what because we have the 0. So we have 1/4, 0 to the fourth, minus 3, 0 squared. So both of these are 0. So we're really just left with this. 3 to the fourth is 81, so it's 81/4 minus 3 squared is 9 times 3 is 27. And if you plug this on your calculator, you should get negative 6.75. So that's it. That's, again, just the shortcut I showed you guys at the end of 5.2, kind of making it a formal section of the book now, doing some examples and the distinction between an indefinite integral where you end up with a function versus a definite integral where you end up with a number. So come on back and we'll tackle section 5.4.